స్టార్ట్ అయితే అది వచ్చేసిందా?
వచ్చిందండి.
పెట్టుకున్నాను బ్యాగ్లో పట్టుకున్నట్టు వచ్చే పని చేస్తాను.
What is this? By the floor? Okay, so then yes. So before so what is this? 1 gain minus 1. So you give the lambda input, the output will be minus lambda. Okay? Lambda d, lambda q. Okay? Then you need the summation by L omega I C Q. L is whatever you got in the filter. Omega is 2 pi times 250. And you have also this value. 2 pi times 250. L comes to L is a constant value based on what you choose. Okay? Then you need ICQ. So L, this is L omega. But you need also times to ICQ. So from your simulation, you just get that one and go to the mass operation. This is ICQ and this is L omega. Or you can use a gain. So you have ICQ, for example, here ICQ, and you can use the gain, which comes to L omega. You calculate it from here, so it will be L omega ICQ. So can be added by this, and then go to VDC. VD. So you have the VD. VD is the voltage of D axis in point of common coupling. So by this assumption, you add VD, dq is equal to 0. Yeah? So that VD was the DC value, will be added here. Not the constant value. You should measure it because when it changes, you should consider the change here. And then you have also divided in mass operation like this, divided by VBC. So this is your DNP. You can proceed by DNQ the same. Is it clear? Okay.
initially you explained one was the main three phase, other one was the DC source.
So, I think one of you made the simulation well. Is the champion. Did I ask you this one? Did I ask you all the current
వచ్చిందేనా సార్ నాకు?
Then you see, because simulation is start from the zero, then it has some data. So if you connect that, you see that the system is no longer.
By using the bracket, we are going to
Yeah,
select the 0.2 or 0.1.
Yeah, you check the connection to see that the data of the synchronization. So, okay,
Hello.
So, does anybody can say my simulation is working well? So, listen to me. You should see when you have a converter and the reference current is current of the load, it means that the converter is going to supply all the loads. So they inject the power from grid to the load will be equal to 0. So if your grid current is 0, it means that the converter is working well or your controller is working well. But if it is not working well, but you believe that, for example, in your case, we see that you follow there, and also for your case, but the problem was that your parameters are not tuned. So for example, copy, Ka, this type of things should be tuned, and then you see that it follows better. So if someone can claim that his or her simulation is working, probably audio can actually make this problem. So I will be happy to see. Otherwise, you can continue later by this one. So, what is the Okay, but later you complete this simulation. Okay, it is important to understand what is happening here. So it means that you still have some current from the grid, yeah? So it should be a little bit cleaner. Because now you have the balance current. Okay? But what is the load current? Load current? Yeah.
Actually, here I was around 0.4, I was using a black and black.
Are you sure that but this is the load current?
Yes, sir.
And why do you use the load current? So it means that your circulation instead of positive you act negative. So instead of you use the compensated load is compensating something. Okay, so the current if it was green it makes sense. If it was green current it was is it green current? Okay, so you made this one mistake with the calculation. Then it is on the other side. So, yeah, look, instead of reducing the current, you increase the current. So it means that you made a mistake for the positive and negative. Instead of you probably use instead of using the I reference minus I measurement, you use the I measurement minus I reference. Something like this. So, nothing. That's it. No, when you for the job, and what the job interview, the person asks, did you pass this course? What did you learn? Nothing. Why? Because the teacher always tried to tease me and I didn't listen. Oh, yeah. He's very important. Okay, your father is your father is after lunch we have a teaching for closing this part, model predictive controller. And tomorrow you have a small graduation ceremony, and also Uday also provide something. But my mission is completed. I mean, it's not completed yet, but hopefully we close my chapter. Yeah. After lunch, yeah. Yeah, just remove the last chapter. Yeah. Predictive model. Yes. Yeah. So, guys, we see each other afternoon, okay? See you. Model predictive, PI controller, and also in the simulation, I was 100% that you could not conclude the simulation in 2 sessions. And the reason is that when we start by the simulation, you should learn that how to start and what is the expectation from the next stage. For example, if you are going to calculate the theta, and then you should see that what is the value or impacts of the theta for the Vd, Vq, or V alpha, V beta. And if you understand that, you can actually proceed in a right way. And the other thing is that when you close the loop, it is almost close to impossible to say that, first try you can make this simulation work well. But then later you see that after some tuning, you can actually get a quite good result, and you can actually tune it in a better way. So this is also important. And then this is why we start from a smaller scale and go to bigger scale. Okay? So this is very important. Then we discuss about the virtual synchron generator. What is the virtual synchron generator, and why we need to probably mimic the behavior of the synchron generator in the control loop of the power converter. And now Darshida is going to a little bit friendly with, as easy as possible, explain that why do we need to have the virtual synchron generator in a state of PI controller. What is the reason that we need virtual synchron generator for integration of renewable energy sources to the power grid? Tell me. Okay. You know, so Lenny, yeah? Active and reactive power. So you mean that without PI controller, we cannot provide active and reactive power, but with virtual synchron generator, we can. Yes?
But it will not provide energy.
Yes, this is the answer. So, we can provide active and reactive power, but the reason is that when we increase the value of the renewable energy in power grid, the share of renewable energy in power grid, we cannot provide the required inertia. Then, as Lenny mentioned, inertia will provide it. And what will we do by inertia, Darshida? Your name is Darshida? Okay. What is the benefit of this inertia? Look at the Abe. Inertia man. So now say, sit down. Yes, it keeps the stability. I understand that, you're stressed. Yeah, I'm a little bit like this. Okay, anyway. So, now you got, okay, we need inertia to keep the stability of the, yeah. So you know 100%. Stability of what? The stability of the power grid. Lenny, what is the stability of the power grid? Do you have something written there? You remind me that person. Okay, look at the. Okay. You're Lenny? Okay. Tell me.
Active and reactive.
Active, you learn active and reactive power, and then do you know this international language test? PI controller, okay. So it was the language topic for the TOEFL test, so or IELTS test, and said that where is the Pakistan? And someone said that okay, Pakistan is located this one, the weather is like this one, food is like this one, and pass it. Then again they said, okay, so now we said that it is better say that where is the India? So the person start to write, India is the neighbor of the Pakistan. And Pakistan is a very beautiful country, this is the food, this is the weather, and then said that, okay, so it's better think about something else, somewhere too much actually different. So that, where is the Brazil? And the person said the Brazil is very far from the Pakistan. Okay? And Pakistan is like this. So now, Lenny said that always active and reactive power, no PI controller. Okay? Anyway, we measured the stability of system based on the voltage and frequency. Okay? So the inertia provides somehow support for the providing a stable operation for the frequency of the system. And we noticed that we can provide also regulation by drop controller for the voltage and frequency and keep the somehow stability of the grid or provide the somehow support and regulate the voltage and frequency of the grid. So now we are going to talk about the model predictive control. But what is why do we need model predictive control? So the reason is that when we have this synchron generator, they provide the kinetic energy, they provide the very stable voltage and frequency for the grid, this conventional synchron generator. But when we reduce the share of the conventional synchron generator and increase the share of renewable energy sources, then system became a little bit less strong, and also the dynamic stability of the grid reduced. So it means that when some problem happens, this conventional generator, like a controller, like a PI controller, are not fast enough to compensate the transient of the system. Okay? So assuming that we have such a case, so assuming this is the frequency of the grid, okay, is 50 hertz. And then your converter is also connected to the grid. And then we have a load changes. And these frequency changes happening. So this PI controller is not actually strong enough to support this port. Okay? So it means that these frequency changes are coming from the backpack. remember, from the load changes. Okay? So this PI controller is not fast enough to compensate these load changes, in fact, support the frequency of the system. But when we use the model predictive control predicts the behavior of the system, dynamic behavior of the system, and has the faster reaction. So instead of, for example, takes 10 minutes to damp something, it takes in 2 minutes. So this is why we use the predictive control. So in this chapter, at the end of this chapter, you will understand the fundamentals of the MPC. You will be able to develop mathematical models for MPC. And MPC means model predictive control. Analyze the role of MPC in power electronics and apply MPC to grid-connected converters. Am I right, Arya? Yes? You will be able to do these things, yeah? I will check. So, now, what is the advantage of MPC? So, if we see that PI controller or MPC, I can say that first, MPC is much more better because it is faster. So let's see what other advantages are available from the MPC. MPC is very logical concept, predicting system behavior over a time horizon and optimizing control inputs accordingly. It's very straightforward. So you have the behavior of the system, and based on that, optimize it and give the answer. Autolab. Predict the behavior of the system. Okay? So, for example, I can measure your weight, your age, your physical activity, and have these information. Then I can actually guess that how much power do you have. Okay? So MPC get the information from the grid or from the system, and based on that can actually predict the next stage. So we see what is the logic. This is not the fault prediction. This is more reaction, okay? So if you have the model of the grid, it provides the next stage or can guess the next stage. It is not 100% correct, but somehow it can be correct, okay? In comparison with PI controller, you always follow the reference. So it means that something happening and the PI controller follow it. So if the current is changing like this one, PI controller follow the current. But in MPC, you predict the behavior of the system. So let's see, and then later we can get a better idea. So, and then MPC offers easy tuning compared to other advanced control methods. So this is also one important thing. When we are talking about the other advanced control methods, what is the advanced? Do you believe, for example, PI controller is an advanced control method? No, it's a conventional method. So, but advanced, like based on machine learning, artificial intelligence, this type of things, reinforcement learning and these type of things, I mean, MPC is much more better. MPC is capable of controlling variety of process. For example, power grid control, renewable energy integration due to its ability to handle multivariable system and constraint effectively. So it means that, you know, beside, I mean, it has some possibility to control different parameters, okay? So, for example, you can keep the operation of the converter
in a way that we have the stable voltage when the fault happening. So it means that it limits the current that converter somehow inject to the grid, because when fault happening, current increased. So it limits the current, and by this limitation for the current, we can keep the voltage more stable. And in MPC, the handling of constraints are conceptually straightforward as they are formulated within the optimization problem. So it means that in MPC, you can optimize something by some condition. Okay, optimize the losses and keep that functionality. For example, current between this one and that one. So you have in optimal function, you can consider this type of functionality and optimize the system. MPC is useful when future references are known or can be predicted accurately. So this is based on the dynamic of the system. We see that how it's possible. But there are some also drawbacks for the MPC. The derivation of control law is more complex in MPC than in classic PID. Yeah, because that one is the linear, this is non-linear. So this is a number of the actually system or a variable or more, so it is more complex. In the case of adaptive control, all computation must be carried out at each sampling time. Does anybody know what is the meaning of this? So MPC happening, actually the analysis happening when we have the discrete. So it means that for each step, we need to again make the system actually running and get the answer. So it is a very time consuming, and you need a very high speed processor. An appropriate model of the process must be available for MPC to function effectively. Otherwise, if you ignore something, the system probably provides the wrong answer. Any questions so far? Arya, is it clear? Yeah. So explain that why do we need actually this drawback? What is the meaning of in the case of adaptive control, all computation must be carried out at each sampling time? Mm-hmm.
So one process at a time.
Mm-hmm.
Like they are being given language.
Okay. I didn't get, but probably 50% correct. So it's like in this time we are here, and we calculate something, and then we go to this step. Again, we should calculate again to see answer. Okay? Yeah, this is easy as easy as possible. So we have two types of the actually control scheme: is a indirect MPC and direct MPC. So in indirect MPC, we have actually modulator, which like a PWM. So we use that one and then provide the signal for the or reference for the converter, and converter will work accordingly. But we have also direct MPC. So for this case, we don't have any PWM. So the switching state function will be created by MPC. Does anybody know how? So, if you listen to me one time, you easily understand it, okay? So this is my converter, okay? This is my converter. So we saw from the simulation that we have a space vector PWM, and it gives the pulse to the gate, and based on that, we inject power to the grid. Okay? So in our simulation, we saw that we are going to compensate the IL. Okay? So we said that our reference is IL, ILD, and ILQ. So I delta I will be equal to IL D minus ICD delta IQ will be ILQ minus ICQ. Okay? Up to here is clear. Am I right? Oh. And then we run the simulation. The expectation was that this should be equal to 0 and this should be equal to 0 if in the steady state if the controller is working well. Yeah? So it means that converter inject the same current as load. So for this case, we have the minimum error, or error is equal to 0. Means that what we expect from the converter is equal to what we inject from the converter. So converter is working well. Is it here? Does anybody can say, I don't know this one? Arya? Yeah, it's clear, yeah? So now the question is that something is clear is that if the reference current and measured current are the same, it means that our controller is working well, okay? So then we calculated the dn alpha and dn beta based on the equation, and then we provide the switching and converter and see that it is working well, very well. Now I remove this part, a space vector PWM. But a space vector PWM is based on the switching state function 1 0 0 1 1 0 0 1 0 0 1 1 0 0 1 1 0 1, and we have 1 1 1, and also we have 0 0 0. So this is the 0 point. We can neglect these two parts. We have 6 operating conditions. Okay? So, assuming that I have a switching state function with this. So I said that my delta I is IL minus IC. I put this one in the converter. The switching is like this one. Switching. So this is the transistor 1, 2, 3, 4, 5, 6. Okay. So this is VA, VB, and VC. Okay, VA, VB, VC. And this is the DC value, VDC. What we have is this one, okay? So when we said that 1 0 0 means that this is on, this is off, this is off, this is off, this is on, this is on. 1 0 0 1 0 0 means that this is on, this is off, and the lower arm off, on. Okay? Is it clear so far? So, I put this one and measured the value of the current. I see that, okay, this delta I for 1 0 0 was equal to 0.2. And then I put this one. For switching 1 1 0, delta I is equal to 0.22. And then I put 0 1 0. This one. And delta I is equal to 18. And I put again 0 1 1. And delta I is 187. And then I put 0 0 1. And delta I is 16. And I put last one 101, it is 23 delta I. Okay? So we put 6 operating condition for the PWM and measure the ID and IQ, and delta I will be this. So what is the optimum operating condition? What is the best answer? So, yeah. So it means that this one is the answer. Okay? So instead of providing switching function based on the order, we optimize the operation of the switching and get the best answer. So this is direct MPC. It means that we provide the switching state function. If you didn't get it, tell me. Is it clear? You see that, okay, this is the objective function, minimize it, and then that's all, the answer. Udaya, do you have any question? No, thank you. I'm a little bit afraid asking a complicated question and then, oof. Okay, good. So, Arya, was clear? Yes? If I ask you to provide the, you cannot, okay? Yeah, why?
Understood the thing that
Okay.
it's the
So you get the routine, that's enough, okay? You just get the why we are going to do it. Otherwise, I mean, later if you want, you can follow with more detail. But the idea is that, you know, how it works. So this is important, you understand the concept. So, MPC control, actually, we basically provide the function for that one. We have the different types of the function, but the most popular one is actually defined here. I can show you how it works. But basically, we use the discrete time because we are going to go from this step to this step. In continuous, it's not based on the steps, time steps. But here we have actually different. The formulation is based on the discrete. So you can get the system in continuous time. The dynamic model is that. But we can convert it to discrete time. It's very easy. We will see how. And we have also state vector, which is the variable, key variable we have. It can be like, for example, di to dt, the changes we had in dynamic model. So this is some things that we have. And also we have some input that provide the input for the system, and we consider the operation of the system based on that. So if we are going to actually present that one, it's like a dynamic model of the system, which in this case we have the dx to dt equal to ax plus bu. And if you remember, we calculate the dynamic model of the grid-connected converter based on the di to dt equal to a matrix times to I plus something times to function, switching state function times to something, okay? So here we have actually that matrix A, matrix B, we have the variable and input. So for this case, you need, again, get back the first of the chapter 3, first part we mentioned that if you are going to design a controller, you need to know what is the dynamic model of the system. So when we have the dynamic model of the system, we can go further. So xt is the actually representing the variable that we are going to control. So it can be voltage, current, whatever you want. and also UT is the control input. It can be switching a state function or some other things. And we have A and B, which is the system matrix that we saw how we can calculate it in the chapter 4. Okay? Up to here is clear, yeah? There we mention, okay. We mentioned something like this. A, this x dot is equal to A x plus B U. Okay? But there, look. We have the dynamic model of the system, and based on that, we can consider the variable and inputs. So this is the control objective. In SPC, the objective function can be divided by this, but we have different other forms. So we can see that, for example, in our control technique, if we are going to provide this model here for the switching, we mentioned the reference value minus measured value power 2. And UCO can be actually any control model. So after that, we have constraint. So it is saying that, you know, this is the function, and the system, for example, or U is based on U max and U min, so it can be between 1 to -1, and X also variable can be between something 10 to 25, something like this. So constraint is important. So for example, in grid forming converter, when we are going to define the fault right through capability, we said that, okay, the current should be not more than 20% more than nominal current of the converter. So when the fault happening, if we consider fault right through capability, in fact, the converter is working well, and the current will be limited to maximum possibility. Otherwise, if we don't consider this one, the converter will be burned. Then we have the prediction model. So it means that in dynamic model, we can consider the state for the next one based on the dynamic model of the system. So in a state of here, we said that dx to dt, we consider that x k plus 1, the next step. So here we see that x in time t k plus 1 is equal to ax t plus k and b u t plus k. So I think this is a little bit just a mathematical equation, so probably it's a little bit a stupid question you don't like, but later we see that it is very easy to proceed. And then we have the optimization problem, which provide the best answer for operation of the system, and based on that we can update the control input. So now we are going to proceed from like a operation of the one simple sample of the actually one MPC, and to see that what is the routine. Is it really complicated? Because lots of people feel that, you know, MPC is very complicated. But if you are not feeling sleepy and listen to me, you will easily understand what is the routine of the MPC. Sit down. You feel sleepy? I will ask you, okay? Very good. So, example 1. Let's assume we want to control the inverter output voltage to match the grid voltage. So we are going to actually connect the converter and match the voltage of the inverter with the grid. The grid voltage is 5 volts. the system dynamic are defined by the following state model. This is the dynamic model of the system. So it's like this, okay? Or like that matrix we had, doesn't matter. So it's shown by this, where X is the inverter output voltage and U is the control signal. The initial inverter voltage is equal to 3 volts. Prediction horizon is 3, and this control duty cycle is between 0 and 1, and the inverter voltage must be between 0 and 6 volts. So these are the constraints. XT and UT are the constraints. Okay? So now we are going to solve it. It's a very actually interesting example that shows that how we can actually proceed or embedded the model predictive in the control of the converter. So, the model we have is without actually answering my questions, okay? So it's better for you and the class listen carefully. You will get back again? Yeah, okay, good. Should we wait? Wait, okay. You know it? Okay, good. So this is the objective function. We notice that we have and this is duty cycle. So you probably know better than you that we need to tune the duty cycle, and based on that, provide the output, okay? So duty cycle between 0 to 1, then can be 0 0.1, 0 0.2, 0 0.3, 0 0.4, 5, 6, up to 1, okay? So now we actually, by random, we said that we start from 0.5, so our duty cycle is 0.5, and we are going to see what is the value for objective function. So based on that, we said that if we replace the value for the x, so x1 is equal to this equation I mentioned here, and then we replace the x1 to x2, so we get the x2. We replace x2 to x3, we get this answer. So objective function, we replaced this value to the objective function. So we see that x1, we place -1, -5, 2. x2, 1, -1, 2. x3, 0, -1, 2. Plus 0.5, 0.5, 0.5. This is the duty cycle for any time. So it's a control signal. So by this, what is the value of this equation? Is equal to 77.75. Okay? So this is if our duty cycle is equal to 0.5. Now test 0.6. If we follow the same, then the objective function are the same, but the only thing is the different from here, which we consider 0.6. So if we replace again with the same function, then we reach to value of the j equal to 75.75 for duty cycle 0.6. So how it can be calculated? So we have this objective function which is always the same. So this is the objective function we had, and for the next one 0.6 also the same, and then we have the same function also, and we replace x1 is equal to x0 plus u0. So u0 is 0.6, x0 is equal to is equal to 3. So totally will be calculated x1, and x2 is equal to -5, -0.5 times to x1 plus u1, and then it goes to next step. So by this we can calculate the value for, look at here, x1 is equal to 0.5 x0 plus u0, x2, then this can be used for the x2, and x3, this can be used to x3. So if we replace in the function, we see the value will be equal to 75. So at least if we are going to compare 0.6 duty cycle 0.6 or 0.5, which one is better? This is 75. This is 75. Sorry, yeah. No, I made a mistake here. It is 82 point. No, it's the same. So probably something happened. Sorry? Now 77 is this one, and it's 75. So if we are going to compare this one, what is the best answer between 0.5 or 0.6? Why? The value is smaller. Okay? So we minimize, our minimum value is that one. And then you can at home try for the 0.7 and 0.3. So we see that 0.7 is 78.3 and 0.3 is 82.0.4. So the best answer between these 4 duty cycle is equal to 0.6. So the answer will be, so if we provide 0. equal to 6, at least we have the minimum error. So, but it doesn't mean that they are optimum. We just consider 4 operating conditions, so it can be more. So now we see that if we have this step, each from 0.1 to 0.2, 0.2 to 0.3, 0.3 to 0.5, up to 1. We see that we should proceed 10 operating condition. And if we go one by one, it means that 0.01, 0.02, 0.03, we get a better answer, more accurate answer, but it takes more time. So we need the more stronger processor to process. It's faster. So this is one thing that we should consider. You cannot say that, you know, my step time is 10 minus 6, but if go to 10 minus 8, it works well. No, processor that's not working in the hardware. So you should actually find the optimal operating condition also for the hardware operation. But one time, again, is there anything that you feel you didn't get it? Is it clear? You see that it has a routine way. You have the dynamic model, and dynamic model provide the next step. So you have the current step, and then go to the next step, other step, like this one. So if your horizon step is 3, you have to consider 3. And if it is 10, you go 10. But the problem is that you cannot predict lots of actually longer horizon because it has a limitation. Any questions so far? No? Yes? Yes, sir. One time more? Manoj, yeah? Okay. Cost function is dependent about what you are going to minimize. So if, for example, switching is minimized, then you can consider the for example, current or voltage. But basically, you consider, for example, voltage of the... so let me give you one example. Assume you have a grid-forming converter. And then the load is changing, current is changing, voltage is changing. Okay? Then a fault happening in the system. Current increase, I don't know, 100 times. Then the voltage goes down, and then it will be unstable, and then outage happening. So for this case, we consider this one as a cost function that the voltage cannot drop more than 10%. So we reference is, for example, if 400, we see that X or V minus 360, this is our cost function, power 2. So it depends on which part of the system is going to be controlled. Or you are going to inject the current, then you can actually put the limitation for that one, so that my current is limited by that. So I minus that limitation is the cost function. So, and by this you can limit lots of things. So you can limit the current, voltage, so you can say, okay, my converter is going to inject maximum 10 ampere, and the voltage should stay in 319. So it's I minus 10, 2 plus V minus 92. So it means that when we find the most, minimum answer, it means that this is the answer, and the answer can be implemented in the control system or in the switching. Any questions so far? Yes, sir. number. Uh, Basically, you cannot go so further. But how should we? What do you mean? Read it again. Okay. And I'm basically. It depended, but you cannot actually say that my horizon number is actually, I don't know, 200, because then the processor is not working well. So basically they have actually some limitation. So you cannot say that go 1 or 2 or you can theoretically calculate it, whatever. And now if you say that go to 10, I can go easily. But the problem is that then you go to where processor, it doesn't work well. Yeah, basically 1, 2, 3, something like this is feasible, but longer no. This Sergio Vasquez from University of Sevilla recently published a paper and used the continuous mode, and I really was surprised at how it's possible with the continuous mode. I didn't study his paper, but they did develop something like this. So basically, it depends on where you are going to use and how much accuracy do you need it. Yeah. This cost function is not for the real system. This is just for the basic actually. But real system we have also similar like this. Okay, the example. Then, but at the end in real system, you should provide by coding. And then anything changing, you should see it. Otherwise, this type of is like the alphabet of the model predictive. Then if you are going to go further, the system will be, for example, in system matrix 20 times 20, and then you cannot calculate by the number, numerical example. Yeah. Weighting factor also depended that what is the rate of the voltage and current you are going to consider. And then one thing is that you should tune it probably by implementing another actually optimization in the control loop, because this weighting factor calculation is not that much easy. So for this, they basically use nowadays one of my PhD students is working in quantum computing to optimize it, then pass it to MPC. Yeah. Yeah. No, you can go further, but at the end I'm saying that the procedure will be a little bit time consuming. Yeah.
It becomes complex.
Yeah. And I'm saying this is very simple example for the understanding. In real system is completely different. Yeah. Okay. So, Udaya, is it clear? Yeah, you like it? Okay, you like me also, yeah? Okay, good. So, now we are getting back to the chapter 4, assuming that our system di to dt is like this, okay? So now we are going to go through the more real three-phase grid-connected converter. So you can put whatever you want here based on the R, L, V, whatever you define in the grid-connected converter as we discussed. But we are going to find the best answer for this system. So initial value is I0 is this one, U0 is this one. And now we are going to solve it. We have two options. One, I explain to you. Second, I ask someone come to explain to us. Abe, you want to, yeah? You were sentences to learn this in the class. You want to prove that? No? Okay, good. You are going to listen? Okay, good. So do we have any volunteer? Okay, no, good. No news, good news from you. Okay, then this is our system. We have x dot equal to a x plus b u. Do you agree by this? We have also this initial current and control output, input, sorry. So then we see that I K plus 1 is I K plus B U K. And when we get back in the beginning, we see that the converter, they use a discrete time state space model. It is obtained by discretizing the continuous time dynamic of the system. So if we get back to this question, this one, yeah, this one. Is it continuous or discrete? Continuous, yeah? So now we need to go to discrete. So I cannot explain how we can, but you can actually use this equation, just transfer this one by this. So discrete of A with AD is by this equation, and BD can be calculated by this equation. So it's like a more actually write the code in the math lab and it calculated very easily for you. So when we have such a dynamic model, we convert it from continuous to discrete. And if these things happening, the A in discrete value and B in discrete value is calculated by this. It's not like you find manually. No, you can use the computer and just convert it and reach to this value. So I didn't calculate it by myself. And I'm not sure that this is correct or not, but this is assuming that this is what we get from this discretization. So this is first step. So it means that when we have the dynamic model of the system, we convert it from continuous to discrete. And the next, we calculate the next stage. So we have A K plus 1 is A K plus B U K. So I K plus 1 is A I K plus B U K. Okay? So it means that if we have the value for K equal to 0, we can calculate the K for 1. Yeah? So we have K for 0, U for 0. So if we calculate I K plus 1, it means that K equal to 0. Means for the next stage of the 0 is 1. We are in 0 and the value is this. For 1, we put this equation. I1 is equal to A times 2 I0, 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 B, D times 2 U0. So we calculate the I K equal to I1 equal to. So we calculate the current for the next step. Is it clear? Yes? So then by the same, we can actually calculate for the 2. So it means that we have I1, and then for K equal to 1, we have I K1, I K plus 1 is equal to A I K plus B U K. So if we go to 2, it means that K is equal 1 plus 1 is 2. Okay? So I2 will be this times to I1 and this to U1. Okay? So by this you can calculate the next step. So you can go to 2, 3, 4, 5, 6, 7 and predict if you are sitting here, what is happening here if you go. Okay? So conclusion. Dynamic behavior. The current injected from grid-connected converter follow predictable dynamic governed by the system state matrix AD and control input matrix BD. So it is very important. So we have actually should consider that what is the best value for the operation of the system. So this is very important. and control input. The control input UCA influence the current dynamic linearly, allowing the converter to regulate injected current effectively. Yes. Does anybody can explain what is the meaning? We have U. U is the control input. Control input. It impacts the current. So if something happened, you can see the current, injected current from the. So what is D? Di to dt is the current variation. So if something happened in the control input, we can see the current variation. And predictable insight. The discretized model helps predict the future state of the system, making it suitable for real-time control application. I cannot say it exactly, but because you can predict, but not for the long horizon, because its processing time is very high. What are you writing? What?
Just taking the sum calculation.
Let me see. Wow. Wow. So can explain to what you write? No, explain it to us.
No, the notes.
Mm.
Okay. So it's the same thing.
So you can explain there.
Because I'm taking down the sum. How you solve the example. The
I
steps.
never forget him rest of my life. Okay? Okay. Yeah, okay, good. But we have this one. This is why I'm going to say. Uday, can you send that file to them? Yeah, they have a stress. Yeah. You have a stress for that one?
Yes, sir.
You have a stress?
In writing.
Mm.
No, I have the habit to write.
Oh, habit to write.
I always write.
Mm.
Like if I
And you study also at home?
sometimes not in last 10 days I have not studied at home.
Mhm.
Honestly.
Okay. Why? Because of that. No, if I look at your actually hand, probably it's very non-linear actually. Give the Hyderabad, Delhi, Mumbai, okay, everybody. Okay, even up, it's impossible. Okay, anyway. So we provide them, but just make sure that everything is clear, we are in the same page. So you see that, we can provide the next stage by using the current stage, okay? So we have T plus 1 is the dynamic model, so AX plus BU. X is something that we are going to control, BU is something that we can apply for the control. So for example, duty cycle of the converter, we can change it, and by changing the duty cycle, we see the value of the current is changing, or voltage. So if up to here is clear, we can go to the next stage, that why is predictive control so attractive and suitable for power electronic. One, we use the switch in power electronic. So the converter or plants we have are based on the discrete. There are also controller which is discrete. So basically this predictive control is working in discrete. So seems that they are very meshed together. And also this is very actually good fit for such a structure that can optimize the behavior of whole system. And the other thing is that this power MPC, they are actually non-linear, but we don't need to linearize it. Basically, we can use it and optimize the answer. So this is why we use it basically in power electronic. So power electronic system operate in discrete time due to their switching nature. So we have also discrete. MPC naturally fit this structure since it works by predicting and optimizing system behavior over a discrete time. So it means that they are matched. And this eliminates the need for continuous time approximation, make MPC a direct and intuitive control method for such system. And no need for linearization. So for the PI controller, we need to actually provide the linearizing it, but in MPC we cannot. We can directly go and find the best answer. It can handle the non-linearities and switching dynamic directly. So we notice that, for example, we don't need them, this type of modulation. And it also can continuously or instantaneously provide the different equations. So you can actually modelize the system with both voltage optimization and current optimization. And basically, the conclusion is that this type of technology is working in the discrete, nonlinear, and also in multiple variables. So what we have in power electronics, it can be actually handled by MPC. So it is pretty much with power electronics. But nowadays, still PI controller are working, and most of the industrial sector are not using MPC, but they notice that they need to use. So for this reason, I know that ABB started to control a drive by MPC. Yeah, this is good news. So later, if Sidams is going to actually present himself, say that I am expert in MPC, I can control it, and if you give this job position to me, then probably I can bring this added value to your company. All right? Okay. So what is the benefit of MPC? Okay. Assuming asking this question that's from Arya. Yeah. So the question is that, do you know MPC? Yes, sir. You said to him? Or written? You don't have actually, you have here also. Look, MPC does not require linearization. You should actually understand it. And believe me, if you are going to be expert person, expensive engineer, you don't need to be first one in the class. You should understand the routine. Am I right, Arya? Yeah. So, Abe, do you have any comment? Do you like MPC? Is it possible I see 3 years later some publication that your name is there in topic of MPC? Yes or no? No? Why? You can, yeah? You're laughing, it means that you will publish something. Yeah. Okay, good. Yeah. So you're not interested to follow this one? You don't know? You don't know where is your place 3 years later. Do you know? You are going to be engineer, you are going to be master student, you are going to be father, or you have no idea? This is a good idea. Actually, the camera is here. We can. So the future can be predicted by 2 types of the people. Does anybody know whom? First, prophets. That we are not. Second, interaction. You can predict the future by this. So, but profit can actually predict the future. Okay? Second, so first, we are not profit. Second, stupid. Okay? Stupid. So we don't like to be also stupid. So we cannot predict because we are not profit and we are not stupid. Okay. Good? Okay. You're shying or your noise is always, your voice is like this? You're shying. Okay. Udaya, why they are not actually speak? Mm-hmm. Ah, okay. Okay, this is the reason. I thought that probably they didn't eat the good lunch, so they have no energy to say, yeah. Okay, good. Yeah. But Abe is a smart guy. Yeah. Okay, good. So now we have actually the model of the grid-connected converter. So this is from the Jose Rodriguez. Actually, basically, he's the big man in this. In switching of the model predictive control. So basically, as I mentioned here, actually we have 8 operating possibility for the operation of the converter. So we have 1, 0, 0. I mean, basically it can be off. So 0, 0, 0, 1, 1, 1. 1, 0, 0, 0, 1, 0, like this one, okay? So we have 8 operating condition started from 0, 0, 0 and ended by 1, 1, 1. So from this 8, 0, 0, 0 and 1, 1, 1 are definitely 0. So the output voltage will be 0. So now, Leonid, you can say that why? Look at here. If we have 0, 0, 0, it means that this is off, this is off, this is off. So it means that they have no outputs. And if we said that this one, 1, 1, 1, 1, 1, 1, then again output will be, because we have 180 degree, 120 degrees, so the voltage are the same, and then it is equal to 0. So we have 8 operating conditions with 7 different voltage vectors, because only 0, 0, 0 and 1, 1, 1, they have the output value equal to 0. But the other 6 one is 1, 0, 0, 0, 1, 0, 0, 1, 1, something like this, okay, as I mentioned here. So for this, we can calculate the value of the objective function, which can be voltage or current, and based on that, we can provide the minimum operating condition and see that which signal or which switching state function has the minimum error, so that can be the best answer for us. Okay? So this is what we use from the MPC, but this is what we are working. We have the actually cost function and we have the predictive model. So we always use the state car as the input, and the output will be the next step. So for the converter also, as I mentioned, you can consider the current, voltage, whatever you want. So we get back again to here. If we get back here, here. So you see that, you know, this is the control input and this is the variable or something that we are going to control. So if we get back here in the just the PI controller we discussed, we see that, you know, we normally want to consider the I alpha or ID and compare with the reference value. So just we use the same cost function or objective function, and based on that we compare with the reference value. So we reference that, okay, I'm going to inject 10 ampere in I alpha and 20 in I beta. Oh? So by this assumption, we reference is like this, 10, and this is also 20. And based on the measured current, we find the best switching state function. You want me again actually explain by this switching? Is it clear or not? Yes? You understand this part or not? You? Abe? No? Okay. I explain one time more. Okay. So, what is this? I alpha minus I alpha star, I beta star, or reference minus I beta. Okay? So this is our objective function. What is saying? Said that we have 6 active switching function. 1, 0, 0. 1, 1, 0. 0, 1, 0. 0, 1, 1. 0, 0, 1. 1, 0, 1. We have also 1, 1, 1 and 0, 0, 0. Okay. But this value is equal to 0. This value is equal to 0. So this is the active signal that we have, switching state function we have. Okay? So we put this one 1, 0, 0 in the converter, okay, or in the switching cost function like this. So we said that, for example, this value we call it J. When J is equal to 1, when we choose 1, 0, 0. 1, 0, 0 means this is on, this is off, this is off. This is on, this is on, this is off. Okay? So we have IA, IB, IC, and then we can convert it to I alpha and I beta. And based on this operating function, for example, 1, 0, 1 means on, 0 is off, off, on, off. Okay? So we can calculate the value of the injected current and compare and replace here to see that what is the value of the J. We can say 1, for example. The answer is 1. And J is equal to 0.98 if we go 1, 1, 0. J is equal to 0.95 if we go 0, 1, 0. J is equal to 1.1 if we go 0, 1, 1. J is equal to 1.07 if we go 0, 0, 1. And J is equal to 99% if we go 1, 0, 1. So We have 6 operating condition and 6 answer. What is the best answer for that one, Abe? Tell me. What is the best answer? 0, 1, 0. Why? We are going to minimize our objective function. And what is the minimum value? 0.95. Okay? So our minimum value is 0.95. So it means that when the switching is 0.10, it means that when the switching is off, on, off, the best answer we have. So it means that our objective function is minimized. So this is the way that we minimize the operation of the system. So we don't need linear control, no need for modular. It directly provides the best answer for us. So by this also we minimize the switching state function and also switching operation, so we have the less losses and better efficiency in the system. So if you look at here, this is the current we are injecting and this is the current for the same system. We see that, you know, when we increase the value of the TS, then in fact the frequency of the switching is less. So when the switching is less, frequency of the switching is less, means that the sampling time is bigger. So for this, the accuracy is not, we have a little bit more harmonic. So if we are going to have less harmonic in the system, we should choose the smaller TS. Okay? So the sampling time will be smaller, but the problem is that then the processor getting the problem because it has the lots of computational analysis and it gives the delay. Our course is finished. Okay? So thank you very much. Thank you very much. Thank you. Okay. So it was a nice course, at least for me. I learned lots of things. Tomorrow we have actually one course, one session from professor, and then you have the ceremony, yeah, and then we can get the certificate and we say goodbye. But I really wish to see you again. I'm really happy now I have more Indian friends, and hopefully we have chance to meet you in Finland. Finland is really good country, and I think it's good that at least you spend some times in the other country and get some good experience. So it's completely different. The weather is cold, here is warm, food is not spicy, it's spicy. People are exactly like Finnish. They are very, Finnish like Indian are very, very kind, helpful. Language is hard, but people are very kind to support. So I think it's good that you have at least sometimes experience if you find the opportunity to visit us. So my email address is here, phone is here. If you send the text to WhatsApp, I can guarantee 99% I will not answer because my WhatsApp number is different and I don't check that WhatsApp too much. But if you email me, I can get 99% I will answer. Okay? So I wish all the best for you, and hopefully you enjoy or learn something good that you could use for the future. Still, we have a session tomorrow, and I'm really happy and sad because I'm happy that I have lots of good friends. I'm sad that I'm leaving, but I have also worked there. So, and if someone failed, don't worry, I will get back again. Okay? Okay. Thank you. Repeat again.
Topic is AC side current control and DC side voltage regulation.
Okay.
We require material for that.
AC side what?
DC side voltage regulation.
Voltage regulation. So we discussed about that one.
Record information for a bidirectional DC to AC converter.
No, we are not actually no, that one not. You're talking about the DC regulation means that, you know, when you have actually this type of renewable energy, they are variable. Then if you remember that I said that, you know, we measured the current and then add in the reference value in the d-axis. So by this you can regulate but regulation of the voltage in DC side. There are lots of other techniques. In our system we consider the balance, but also if you need, probably you can email to me. There are some equations that you can consider for. But then even in the exam you see that the one efficient way is to using the storage devices. We are not going to talk about the DC-DC, I mean bidirectional DC-AC.
By using DC to AC inverter,
Mm-hmm.
when the generation side voltage drops or the generation side power drops,
Mm-hmm.
here we are going to feed the batteries from the inverter itself.
Yeah, I know.
For that we are going to consider that DC bus link voltage as one of the reference.
But you are not talking about the bidirectional DC-AC converter control. So okay, but we are not. We didn't have plan for that one. Okay, and this is not the topic that you could explain easily. But it is not something too much different, because when you go from the AC to DC, you need also the same dynamic model, and the equation is again. You use, if you remember, SVDC is equal to AC, and you have the also other side for that one. So what I can advise you, I mean, I don't know why you're looking for that one, but this is not something different from what we discussed.
Sir, actually energy management technique is there.
Energy management is?
Energy management control, overall.
Mm-hmm.
In that many optimization techniques is there, sir.
Yes.
But in real-time implementation, they say very less real-time implementation is there.
Mm-hmm.
Is it work out to do my research towards that?
Mm-hmm. So this is your research, okay? This is not the part of this course. But energy management system is not that much complicated that you make your life very complicated for that one. So for example, you use the energy management system. So how many control level we have? 3. Converter control, frequency and voltage, and EMC, okay? So EMC is based on the situation of the generation, converter, consumption, okay? So sometimes from generation to consumption, sometimes from consumption to generation, like a electric vehicle. I think that your project should be something related to charging a station, and yeah, okay. So this is why you are asking. Yeah, but then you get some signal for that one, and it's like a upper level of the control, and based on the objective, so it can be price perspective or stability perspective. And at the end, you need to control the converter interfacing the vehicle to the grid or grid to vehicle. Okay? So vehicle to grid can be something what we discussed, because we have the DC and then we have the AC also. But the AC to DC also is a rectifier, so you can consider. But if you are going to also control from the AC to DC, again the same dynamic respect, exactly the same dynamic respect you need to consider. So if you try a little bit, probably you find the best. I had recently one new PhD student. In less than 2 weeks, he closed the simulation by PI, and just from the AC side to DC side. Yeah, but I don't know if there is. I tried to follow what I promised. I don't see something remain that I could not refer to that one. Am I right? Yeah. Okay. So see you tomorrow, guys. If you need something, tell me. Yeah, have a nice evening. No, you go. Signature from me? From me? Okay.
And then
I should sign. Sign what certificate? All of them? Oops.
and then what time can we meet? Dinner, special dinner.